you very much. Yes, so I actually started working on directly imaging planets around other stars about 10 years ago. But actually I won't tell you much about my own work. I'll just explain you how do we photograph these things, how do we photograph these planets around these other stars, but then in more general terms. So philosophers, humans, we've been thinking about the potential, how unique our Earth is and the potential other planets around other stars for many millennia. Here are some famous quotes from one of the old philosophers. So here's the Greek philosopher Epicurus, who said that there are infinite worlds both like and unlike this world of ours. And in the 13th century, Deng Mu, a Chinese philosopher, said, well, this is the English translation, somebody made it very prosaic, how unreasonable it would be to suppose that besides the heaven and earth which we can see, that there are no other heavens and no other earths. I believe this one is much, much shorter. Much more direct. And it goes even further. Even as late as the 16th century, there lived a philosopher, Giordano Bruno, who said that there are countless suns and countless earths, all rotating around the sun in exactly the same way as the 7 planets of our system. And so even, well, a bit shockingly, in the 16th century, they burned him for his philosophical views and his argument with the church about his world views and his religious views. These philosophers, they said these things because it matched their worldview. For instance, Epicurus, he was an atomist, so he believed that everything was made out of small or indivisible particles called atoms, and he believed there was an infinite amount of these, so it was very easy for him to assume that there were also infinite things like Earth. But of course, these philosophers, they never had the opportunity and the scientific tools to actually put this to the test. But only 10 years after Giordano Bruno was burned alive, the first telescopes ever invented were used by Galileo Galilei to discover moons around Jupiter. And the discovery of these small point-like objects in motion around this planet, it kind of validated the philosophical remarks made by the philosophers in the many years before. So it's quite shocking that this was only 10 years apart. And even within 10-15 years after this, they had also discovered that the surface of Jupiter is not just a flat thing. It actually has cloudy band structures, and even a red spot was discovered by these early astronomers. So nowadays, astronomers, we can make more structured questions. We can assemble these. We can ask ourselves, how do planets form? Is our solar system common, or is it very special? Is the Earth itself, is it unique, or can we find similar things like Earth elsewhere in the galaxy? And lastly, is there life elsewhere in the universe? So with astronomy, we hope that we can answer these questions, and in particular these questions, we think they can be answered by studying exoplanets. It might not come in the next few years, but we think that to all of these questions we can probably find an answer in the coming, hopefully in the coming 30 years maybe. So why would you photograph planets directly? Maybe you've already heard about other methods to discover planets around other stars. So why do we want to do this? Well, by directly photographing these exoplanets, we can do three things. first we can find planets that are very far away from the stars, unlike the other methods that kind of focus in on planets close to the star. To find young planets that might tell us how planets form, and to directly study the atmospheres of these planets, which means either thermal radiation being emitted by the planet itself, or reflected light from this planet, that reflected starlight that gets reflected off this planet and picks up certain atmospheric signatures that we can use to tell whether there's some kind of special gas in the atmosphere of this planet. And astronomers have already imaged various planets directly, and I'll show you a few examples first, and then I'll go into the details on whether it's easy or hard. So one of the most spectacular results is this star, which is called Fomalhaut. It's one of the brightest stars that we have in the sky, in the constellation of Piscinus Australis. And this star has been covered by some kind of tool which reveals a large circular ring of dust around this star. And this by itself is already quite spectacular, and it kind of looks like the Eye or Sauron of the Lord of the Rings movies. But if you look in this corner on the bottom right, there's actually something, a little point, and people have tracked this point seemingly going around this star with the Hubble Space Telescope. Already in 2004 they looked at this star, and well, they were quite intrigued by it, because you have this nice dust ring, and the inner edge of this dust ring, it looks a bit sharper than the outer edge. So you know what? Maybe this is a shepherding planet. So like a shepherd guiding the sheep, this planet is guiding this dust ring and keeping the dust ring in its nice truncated shape. Well, people have monitored this supposed planet for years on end since this original detection, and first they thought, well, it seems actually that it's not on the inside of this dust ring. It seems that it wants to cross it. If you look into the future, it seems that it crosses the ring, which would destroy this disk. And it becomes even worse. People kept on tracking it, and eventually we lost sight of it. It completely disappeared out of view. And what people now think that is happening, that it's actually a dust cloud caused by two very large asteroid-like particles, or kilometer or hundreds of kilometers size objects. When they collided, they created a massive dust cloud very locally, and this dust cloud just grew and grew, and while it was growing, it became tenuous, it reflected less and less light, so eventually disappeared from view. So at the moment we don't really see a planet anymore. So, but it does show us, we can, even with this direct method, we can already see beautiful rings, debris disks around these planets. Around these stars. And maybe the most spectacular object that we have imaged directly is the system HR 8799, which is in the constellation Pegasus, which is also visible by the naked eye, just like Fomalhaut is. And here, astronomers initially discovered, using this direct technique, the outer three planets, and then later when they went back, they discovered a fourth planet, the innermost planet. Now all of these planets, they're so big, they're about 10 Jupiter masses, so 10 times as heavy as our planet Jupiter. And so they're almost as heavy enough to become a star themselves. And if you put this on the scale of our solar system, all the planets until Saturn, they would fit into this inner mass close to the star. So you're actually seeing planets that are quite far away from the star. Now, what makes this so difficult? Because it seems that we have imaged a few of these objects already. Well, there are a few reasons. So first of all, we need to be able to separate the planet from the star, so to separate them into two distinct objects, not just one. Secondly, we need to correct the turbulence in our Earth's atmosphere, which creates murky images, like out of focus images. Thirdly, we need to suppress the starlight, so to make sure that the very weak signal that we get from a planet is more important than the signal that we get from the star. And lastly, we need to be able to separate the planet's light from the starlight, because they're so close to each other, they're overlapping, so we need some kind of black magic box to separate them into two solutions. So I'll go through each one of these problems step by step to show you what our solution is. But first I need to understand some of the things that I'll show. I first need to talk about something called the diffraction limit, or diffraction pattern. So if you're looking through an optical system, whether it's your eye, or it's a camera, or it's a telescope, however small the objects are that you're looking at, it will always be impacted by a certain pattern that's just engraved essentially into the optical system that you're using. It's due to the limits of physics, we have to deal with this. Now, every single object that you look at will have this pattern of concentric rings, and we normally don't see this pattern because it has such a tiny angle that we barely notice it. But I know that some of you are wearing glasses, so it means that if you take off your glasses, the diffraction pattern that you have is so bad that it impacts your eye, it impacts your view on the world. So you went to the optician, you bought a pair of glasses to restore, to get as close to this nice, beautiful round pattern as you can. So for some, including myself, this laser point might not be a nice point. It might be a stretched out spot or two spots. So if you look at two objects that are very close to each other, there will be some kind of distance, the minimal distance that you need to put them at before you will be able to tell us, yes, this is definitely two objects. If they're too close to each other, you would say, nah, this might be just one object. And astronomers use this diffraction limit to essentially gauge how small the things are that we can separate. Now, of course, if this diffraction limit is always impacting us, we wanted this diffraction pattern to be as small as possible, to span the smallest angle we can imagine. And we have some ways of improving on the size of this diffraction pattern. One of them is to decrease the wavelength. So this means looking at things in bluer light. And the other thing is that if we build a bigger telescope, if we increase our telescope diameter, we also get a smaller telescope diameter. We would get a smaller diffraction pattern. So the smaller the wavelength, the bigger the telescope is, the easier it is to separate two objects very close to each other. Well, what can astronomers do? Can we easily decrease this wavelength? Well, not really. If you're trying to observe certain molecules, if we want to detect life on this other planet, we might think we want to have water, we want to have oxygen. Well, we are stuck to using specific colors of light, especially the infrared. Also, if we would choose to use bluer light, then the star becomes actually much brighter. Like, if you look during the day to the star, it looks a bit yellowish, whitish, so it emits most of its light invisible. And if you look at a piece of iron that has been in a fire, it might glow a bit red. Just like a planet, planet is much cooler than the star. So if we look in the red, the planet, if we look in red wavelengths, the planet is bright. If you look in bluer wavelengths, the star is actually the brighter one. So it actually becomes worse to go to the blue end. Now, this effect of atmospheric turbulence that I've shortly mentioned, this turbulence is worse in bluer light, so we can't really change this wavelength. We have to use the tools that we have, the colors that we have. But we can actually increase the telescope diameter. Now, until recently, the biggest telescopes that we built, they had a mirror, a monolithic piece of glass, one piece from one side to the other of 8 meters in diameter. But these telescopes become really heavy, so heavy that it's difficult to point them at stars. It's difficult to build them, it's difficult to use them. But nowadays we use segmented telescopes where this large mirror is carved into roughly 1 meter sized mirrors. The mirrors are much thinner than in these monolithic mirrors, so they're cheaper to build. It's easier to make them into a very big telescope like this one. And these, nowadays, they're 10 meters wide. And we expect in the future to be able to do the same, but then make them 25 meters wide. So that's probably bigger than this room. So this problem is solved. We need to build bigger telescopes. Now the second problem, to correct the turbulence in the Earth's atmosphere. How do we tackle this? So this is what the turbulence looks like. It's almost like clouds passing overhead, and if we look with our telescope at any star, any object, even planets, it looks like this. And this is real time, so if you go to a telescope, look through it, it kind of looks like this. If you don't do anything about the turbulence, so you don't really see a nice center. You're not sure where the star is here. It looks like like nothing. So in order to correct this turbulence, we use some systems, some optical mechanical systems called adaptive optics, where we have this distorted wavefront of light coming in from the atmosphere, which is reflected by a deformable mirror, and then it's sent to our camera. Now, when we image it with this camera, it looks like this. It looks like a mess. But we actually have a second camera here that can sense the turbulence. It senses how distorted the wavefront is, and then it can send this signal back to the mirror, and the mirror will apply the opposite distortion to this incoming wavefront. So eventually the wavefront will be flattened by this deformable mirror. So when you look through this camera, which is just like this camera here just in front of us, or your webcam, regular camera, the turbulence goes away. So this is a real image from a real telescope, one of the biggest in the world. First you don't see anything, you saw this big blotch, but now you can see this big thing is actually two objects close to each other. And these are two small, tiny stars. One is probably orbiting around the other one. We would never have known it if we didn't use the adaptive optics system. So there was a massive improvement in the sharpness of this image from the adaptive optics. So if we compare them side to side, first you will have a deep blob like this. That's the image of the star that is distorted, and then afterwards the image is corrected, and you see all the light is concentrated into one point. So if there's a planet sitting next to it, it will be much easier to see here than in this case. So the solution to this turbulence would be an adaptive optics system. Now the third difficulty that we have is the star is so much brighter than the planet. It's about a factor of 1 billion brighter. So you could compare this to the amount of light coming from a firefly next to a lighthouse. Or, for instance, if you're trying to express the height of Mount Everest into blood cells, how many blood cells do you stack on top of each other to reach Mount Everest? So it's a massive difference in brightness that we're dealing with for a planet like Earth. So how do you get rid of this starlight so we can actually see this faint planet next to it? Well, we use a device called the coronagraph. And a coronagraph can be as simple as just sticking your thumb in front of the star blocking the light of the star, and then some of the planets might be revealed. So with I made here a simulation of a star with a planet around it, and the chronograph is sitting right here, and it's slowly aligning with the star. And the star is getting dimmer and dimmer, and then maybe you saw a little signal, a planet signal being revealed. So the chronograph is sitting here, and the star is slowly moving behind this chronograph, this optic, and we can see a small planet here. So with perfect alignment of this chronograph on top of the starlight, you can perfectly get rid of the starlight. And these chronographs, they're pieces of glass. This one is about a centimeter in size, and this one is put exactly in the middle of the starlight to reveal the star. But this is an idealized case. In reality, we have to deal with the crap of our telescope and the Earth's atmosphere. So a corrected image of the star might look like this, where you have all the light sharply concentrated in the middle. If we put a coronagraph on top of the star, then you can see that these concentric rings are removed. So this image on the right looks much darker to an astronomer than this image on the left. So a planet would be revealed in this case. But of course you can see, because this is not an ideal case, there's still a lot of junk going on here. And for this we have to use a final method. How do we separate this planet light, the remaining planet light, from the starlight? Well, we use a reasonably simple trick. We use computers to do this for us. So here's an image of a star, Beta Pictoris it's called, and this is an image of a nearby star, which, I don't know, it's some random star, we didn't even give it a name. And if you look very closely, this diffraction pattern that we were talking about, for both the interesting star and the not so interesting star, they kind of look the same. There are some similar lumps and bumps. So using the computer, we subtract this image on the right from the image on the left, and what we see is a small difference. So there's actually an object sitting very close to this star, which is actually a planet, Beta Pictoris b. So we use much more complicated methods nowadays. This is one of the easiest, and what we're exploiting is things like changes in the color of the planet with respect to the star, or that one star might have a planet while the other one doesn't, or maybe the planet moves around the star, so it will be in a different location. So if you subtract the two, you will see the planet. So this fourth solution is computer codes and diversity, time diversity, angular diversity, spectral diversity. And with all these techniques combined, the state of the art that we can do is actually the following. So these are all kinds of stellar systems with planets, and you can see if we track them year on year on year, they're actually moving around these stars. So here the system HR 8799, you can see these 4 planets are orbiting around the star. The inner one is the quickest, and then the outer one is orbiting the slowest. And this is Beta Pictoris b, that actually, it went closer and closer to the star. It appeared to be closing in, and then it passed by, and it came back on the other side. And this is 51 Eridani b, and this is actually one of the smallest planets that we have seen with the direct imaging method. It's only 2 Jupiter masses. So compared to the 10 Jupiter mass planets of this one is much smaller, and it's actually much cooler. It's about 700 degrees Kelvin. So this is some of the best things that we can do right now, and in the near future, and the near future is coming fast, we will build this 40-meter telescope, the biggest one ever, 4 times bigger than the current record. we will have this instrument especially made to do this kind of work, to suppress the starlight and to be able to discover planets. For the nearest M stars, we would be able to see Earth-sized planets. And Taiwan also has a contribution in this instrument, so you'll hear more about MITIS coming from ASIAA very soon. So thank you very much for your attention. So if you have any questions, then the floor is open. Thank you.